this is basically a very short version of my PhD defense that I gave about a month ago on persistent autonomous maritime operation with an underwater docking station. So jumping right into it. The ocean is a very important place for daily life. It's large, very diverse, but we really don't know that much about it. If we consider just the topographical level of mapping, so let's say elevation mapping in the ocean, we have good detailed maps of less than 5% of the ocean, whereas there's good detailed maps of the moon and Mars that you can just get on Google Earth. So basically, we don't really know much about the ocean. And this is primarily because sensing in the ocean is very challenging. So typical sensors have a range of a few hundred meters or a kilometer at maximum range. And basically it makes it so that we have to deploy a large number of vehicles to actually achieve any sort of goal. One way to do this is to utilize autonomous underwater vehicles with the support of manned surface vessels. So basically a manned surface vessel will go out in the ocean, deploy somewhere between 2 and 10 of these autonomous underwater vehicles. Those vehicles will operate for 12 to 24 hours doing a survey, and then be manually retrieved, recharged, and retasked. But still, you need to have that manned surface vessel, which costs in excess of $30,000 per day to actually operate. So any sort of large-scale operation is just basically infeasible. For very specific missions, autonomous underwater docking is a feasible solution using current technology. These docking stations shown here are the most common type of docking station. It's basically a large funnel design. And with these docking stations, the vehicle comes in, bumps along, and is docked. Each of these stations is highly capable of being or supporting persistent operation, but they're each in excess of $1 million, are seafloor mounted, and only support a specific kind of vehicle. So that means that it would be equivalent to a gas station that doesn't support different makes and models of vehicles. Basically, it's an infeasible solution going forward. And that led us to develop our own docking station, which is the Adaptable docking station. Basically, we realized that autonomous underwater vehicles are very good at controlling their depth. So we can simplify that design down, that 3D funnel design, into this more planar design, and then go in and dock to this docking station. But how did we actually get here? First, we had to model the system using hydrodynamic and impact forces. The hydrodynamic forces are modeled based on viscous hydrodynamics, which is basically terms based on velocities, angle of attack, that sort of thing, as well as the inviscid hydrodynamics, which are based on vehicle inertia, added mass, basically things that resist acceleration. Impact dynamics are modeled similarly using a third-party software. And using these two terms, we can go and then do a design optimization to optimize the overall docking station design. And that docking station design was optimized over several hundred hours of computation and validated with 2 different size platforms to basically yield or lead to this result, where the vehicle comes in, bumps along the docking station, slides in, and is docked. And as I said, we've validated it in simulation with a 10 kilogram size vehicle as well as an 80 kilogram size vehicle. And these 2 vehicles represent the wide majority of actual autonomous underwater vehicles in the field. So now that we know how the docking station is designed and modeled, we need to actually be able to implement it and navigate in the real world. Navigation in the real world for these vehicles is typically broken into 5 stages. There's the en route stage, which is basically the vehicle manufacturer controller doing basic scientific survey waypoint missions. At certain points through the mission, it will switch into what's referred to as backseat control, where we will take over with our custom controllers to approach or set up the approach and approach. And by that, I mean that we will navigate from the field towards a point that is directly in front of and directly pointed at the docking station. At that point, it'll switch into terminal homing, which is based on optics for the minor high rate adjustments that are needed to increase our capture rate and lead to eventual docking. For our approach setup and approach phases, we're going to utilize a look ahead or line of sight controller, which is a very well understood common controller in maritime applications. The one challenge of these controllers is that they have trouble with discontinuities, especially discontinuities in location of the vehicle. Basically, they lead to instability of the controller. So we need to be able to handle those discontinuities, and we're going to do that by basically modifying the path that we're trying to return to, utilizing Dubin's set. So basically, in 2 dimensions, these autonomous underwater vehicles can be considered to be a Dubin's car, capable of turning up to a maximum rate. And that means that the solution to go from any point and orientation to any other point and orientation is always going to be this Dubin's curve, which is an easily calculable set of turn straight turns or turn turns to actually solve this path. So now that we know those 2 things, we can go and combine them into a overall navigation controller that can handle discontinuities for positioning of both the vehicle and the target, as well as handle reattempts on missed docking approaches. And that leads to the overall approach method, where basically we switch into backseat control, measure our distance to the prescribed path. If that distance is large, then we measure our distance to the previously augmented path. And depending on the result, we generate a new augmented path, use the old path, or use the prescribed path, and then follow that path using integral line of sight until we reach the end of the path, at which point we switch into terminal homing. For our terminal homing system, we're utilizing a very computationally efficient method. And the reasoning for this is that autonomous underwater vehicles are very computationally constrained. Basically, they don't have power, they don't have the capability to do very intensive calculations. So we're doing optics based on a very simple brightest pixel approach. So find the brightest pixel, put it in the middle of the frame, use PID to control our rudder. Very simple, but very effective in the field and in changing water conditions. So now that we know basically our approach, our control, and our actual design, we need to go and simulate and test in the field. And this is where the bulk of the work has been, is in the simulation and field results. So for our simulation, it's set up at a 100 Hertz timescale, with the controller replanning at 2 Hertz. That's on the order of our controller frequency in the field trials. And basically these simulation results are going to be broken into 2 steps. The first step is this approach phase, where basically to validate the approach controller, I have it going around this blue path. The blue is the prescribed path that it's trying to follow, and then comparing the proposed method, which is this augmented method, with a more classical method, this integral line of sight method. The important thing is the chart on the right. You can see that both the proposed and the classical method converge at nominally the same rate. However, the proposed method is much better in rejecting these overshoots when there's no disturbance. When there is some disturbance introduced, a realistic disturbance of 0.1 meters per second in both directions, we have similar performance of the traditional method, where it has this overshoot pattern, while the proposed method is able to reject those disturbances. If we try to introduce a strong, basically not realistic disturbance, you can see that both controllers have more trouble with this disturbance. However, the proposed method is still able to maintain less than ½ meter of cross-track error for the majority of operational time. And the overall result is that the proposed method shows a 2 to 3 times improvement compared to the traditional method when considering the cross-track error over this trajectory. And that is important because basically that will mean that we can always deliver the autonomous underwater vehicle to a handoff location for our terminal homing system. And for our terminal homing system, we're using this very simple approach. Here's the results in simulation. The important thing is that if we consider a wide range of disturbance currents, so basically scattered everywhere that would be at all feasible to happen, we can see that the controller is best at actually docking when there is a slight head current. And the equivalent to this for like aircraft will be that you're more effective at landing an aircraft when there's a slight headwind versus landing in a tailwind is very hard. Landing in a strong tailwind is basically impossible. And again, landing in a very strong headwind is also very challenging. But the best scenario is just a slight headwind to land in, which makes sense based on experience in other domains. And that leads into our field results with this system. So basically the field results I'm going to talk about in two stages. We have the approach phase and the terminal homing phase. They are disconnected at this point in field, but are being worked on to integrate into one system currently. For both systems, we're utilizing what's referred to as a front seat, back seat control strategy. And by this, I mean that basically the front seat controller is from the vehicle manufacturer. It does sensor fusion. It creates a vehicle state. It estimates all positions, controls sense, controls actuators, that sort of thing. Does waypoint navigation. The positioning and that sort of information is sent over an Ethernet link to our backseat computer, which is a custom robot operating system setup where we go and we take that vehicle state and go and calculate different commands to send back to the vehicle. And with these two systems combined, we can achieve a wide range of things, such as extended autonomy testing. So going and having it go around this pattern in the Fairfield Lakes Pond nearby. If we pull out a single trajectory around here, you can see that we're submerged for the vast majority of the time, surfacing at relatively consistent intervals to get GPS localization. And then over the trajectory, the majority of the time we're within 1 meter of cross-track error, which is on the order of what was simulated based on the simulation. If we consider the virtual handoff testing, so basically how can we approach this handoff point to switch into terminal homing, we can show that in every single tested scenario, so this one went around this track, I think it was 49 times. In all 49 scenarios, it was less than 1 meter of cross-track error for all the tested scenarios. And that less than 1 meter of cross-track error is significantly smaller than what was tested for our terminal homing system. And with our terminal homing system, we tested with up to 4 meters of cross-track error. So basically this implies that our overall experimental success, once these two systems are combined, will be very high, on the order of 70 to 80% success rate. But when you combine that with the reattempt ability of our planner, it will quickly drive the success rate to near 100% in the field. And that gets into the actual videos of our docking system. These are probably the best way to actually explain how everything works. But basically you can see that the vehicle is coming in here. In this case, we released it from relatively straight in front of the docking station. So you can see it comes in, slides, and is docked. Once it's in the docking station, we're working on integrating the power electronics to actually recharge. But basically, for now, it's just getting into the docking station. In this one, we're releasing with a 4 meter cross-track error, and the very simple single brightest pixel approach is quickly able to correct for that 4 meter cross-track error and navigate the vehicle into the docking station from across the pool and go in and successfully dock. We also tested docking to a small inflatable boat rowing around in the pool sort of randomly. And again, the very simple approach is capable of navigating towards the docking station with good success rate. In all of our pool testing, we had about a 70 to 80% success rate. In open water, it was nominally similar as long as we released it within vision range. So here you can see the vehicle is going to come in. It's going to actually come in a little bit sideways, but due to the flexibility of how everything is designed and simulated, it actually causes everything to rotate and eventually successfully docks. As we transitioned to open water, this is in Lake Superior. You can see that the vehicle comes in and is able to reject any sort of disturbance from the wave state, as well as disturbance from the boat actually moving in the wave state to successfully navigate in and dock. You can see here everything is moving up and down in the wave state, and it doesn't really matter for the overall docking efficacy. And here it's coming in from relatively far field. You can see the docking station from about 10 meters away in this water clarity, and then come in and successfully dock. So overall, we also had one result that was particularly interesting. In this result, you can see the vehicle is coming in from across the pool. It's going to come in a little bit high We were still tuning our depth controller at this point, but it's coming a little high. It's going to bounce and it's going to pitch down, go down, and then come back up into the docking station. And basically this and all of our other results have indicated that the simulation and experimental results line up with very good accuracy, which is a reassuring sign. So that gets into the overall contribution. And basically the biggest contribution is that this underwater docking system can enable a new concept in AUV operations. It's been designed and validated with a very simple control strategy and is capable of supporting a wide range of vehicles. We simulated with a 10 and an 80 kilogram vehicle, which represents the majority of vehicles in the market. And then the tested control strategies for both approach and terminal homing are robust to changing scenarios, changing conditions. And work is currently ongoing on transitioning some of the work from the small vehicle to this larger vehicle shown in the video here. And that has been my work on persistent autonomous maritime operation with an underwater docking station.